VIP. Let's kick it.
Hello, AP Calculus students. That's right, ice baby, Mr. Record here. We are talking about an e-learning day today going on all over Avon Community School Corporation. And we're glad you're tuning into this video to learn a little bit about the trapezoid rule. If you're watching this outside of Avon on YouTube, it's likely that it could be in the middle of the summer. And ice baby doesn't make a lot of sense to you. Anyway, so whatever the case, I hope that you get a lot out of this particular video. It's actually the first of a two-part series of videos over this idea of the trapezoid rule or the trapezoidal sum that can be used to approximate the area of a curve. It's a very prominent piece of information that is has been very routinely found on the advanced placement exam. And the problem that I think is a lot more sort of conducive to like what you would be seeing on the actual exam is more probably going to be along the lines of what example 9 discusses. But going through this particular example first is probably going to better your understanding of example 9. The example 9 video, if you're watching outside of Avon, is on my channel, and it's entitled something along the lines of the trapezoidal sum with unequal partitions. But in this particular example, we're going to use a trapezoid rule to approximate the area under the function f of x equals sine of x and above the x-axis on the interval 0 to pi, and we're going to use 4 trapezoids. So you can see I've got the picture drawn, I've got it set up, we're just about ready to embark on this, but before we do that, I'm going to back up a slide and formally introduce this concept called the trapezoid rule. If you look at this formula, the very first thing that you're going to want to do is probably run away. There are a lot of things going on with this formula, and this dot 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 here in the middle just means those things are going to continue to go on and on and on and on depending on the number of trapezoids you have. But really the bottom line is that this is a pretty basic, easy to understand formula. But as I said before, as far as preparing yourself for the advanced placement exam, it's not really necessary that you know and use this particular rule. You can use the ideas behind this rule and apply them to any kind of trapezoidal problem, whether you have equal partitions or not. This rule is very specifically designed for a situation where you have equal partitions or equal heights of your trapezoids. So the first thing that I want to sort of get out of the way here is, what is a trapezoid? Well, by definition, a trapezoid is a quadrilateral with one pair of parallel sides. So you can see in the picture here to the right, we have such a trapezoid. And we also know that the area of that trapezoid is calculated by taking half of the sum of the bases multiplied by the height. Now, I kind of chuckle when I look at these trapezoids because they're sort of oriented in a very unusual fashion. They're sitting on the height rather than one of the two bases. And one of the ways that you can think about this is that the trapezoids sort of look like these outhouses. Now, if you don't know what an outhouse is, you probably are going to have to go and ask your grandparents, because I doubt your parents probably ever used one at this stage in our civilization. But that's what I think of sometimes when I see the trapezoids that we come across in our trapezoidal rules or sums. Now, where does this formula come from? That's a great question. Well, if you think about the b minus a portion over the n, b minus a over n, if you've been working with your Riemann sums up to this point and you've been calculating some areas of rectangles, it's very likely that you probably recall that the width of a rectangle that you'd used before is always going to be calculated by b minus a over n. It's basically the difference between the left endpoint and the right endpoint divided by how many shapes that you're going to have. The only thing that's different now with the trapezoid is that this is going to take the place of our h. Instead of the width of a rectangle, we would have a height of a trapezoid along the x-axis. Okay, so we have this guy taken care of, the h. Well, it's pretty clear then, if we look at this 2, It's coming from the fact that there is a 2 in our denominator, or a 1/2 factor that we're multiplying the sum of our bases by. So that must mean that everything else that you see in this formula must be the sum of the bases. And that's exactly what's going on. But it's very interesting in that you see some of these bases, like the first one, with a multiplier of 1 in front, but so many of the ones in the middle, in fact, all of the ones in the middle, have a multiplier of 2, and then you come up against this last one, and he's back to having a multiplier of 1. Well, the reason for that is very easily explained. First of all, I want to buy into the fact that the f of x subscript 0 is the same as a. And the f of x subscript n, think about it, what do you think it's the same as? Nice job, you're right, it's b. Now, it's easy for a student to look at that and think, well, why did they just say a and b? Makes a lot more sense. I'll agree with you, it does make more sense, but by using the x and the subscripts, we're able to start this really nice pattern, starting with x sub 0 all the way to x sub n, which would in fact coincide with the number of rectangles, or I'm sorry, the number of trapezoids that we're going to use. So that's the reason for the fancy notation. Now, as far as why do we have 2's in front of the interior pieces and not the exterior, the best way to demonstrate that would be if I could pull up my calculator here. Now, this is a TI-Nspire CX-CAS calculator emulator. If you're at a school that doesn't use this particular model of calculator, fear not, you're going to be able to understand what I'm trying to show you. I'm not going to use this to do any kind of fancy calculations, but I'm just going to use it so that we can kind of understand what's happening. So just kind of the basic ins and outs of this particular program called Riemann Sums is we have a function, and I've just made up some arbitrary quadratic function. It's the default function that I use for this program. And we can see that my A and my B, I've locked them in to be at 2 and 4. And what's really neat is I can't actually move them if I wanted to, but for the purpose of this video, I'm just going to keep them at 2 and 4, as you can see down here. Okay, I know there's a lot going on with this particular screen, but just kind of pay attention to the things that I'm focusing on. Now, I've set up the number of trapezoids to be, well, I wanted 6, but I see 5. That's kind of interesting because there's sort of a rounding issue that's going on with this, so no big deal. If I just kind of tweak this a little bit, I think I can play around with it enough. Hopefully, I can play around with it enough to get it to match. And there I go. There's 5 shapes. I'm going to take it back to trapezoid, and I've got 1, 2, 3, 4, 5. It's kind of an interesting anomaly with this particular program because of a rounding calculation that's being done in the background. So oftentimes my students may have to tweak that just a little bit. So I have my 5 trapezoids. Well, do you agree that these are trapezoids? Certainly you would, because you can tell that the vertical strips that we would normally draw downward from the curve to the x-axis are capped off by a straight line from one tip of the vertical strip to the other tip. And we keep doing that, so on and so on. Now, if you compare that, let's say, to a right Riemann sum, which is what I have when I dial this back to the dark blue, these are right Riemann sum approximations, as opposed to the left Riemann sum approximation, where we cap off each rectangle on the left side. And while we're here, I could slide this over to midpoint, and you can see the midpoint approximations. Now, if you're students in my class, I know that we spent a little bit of time going over the basics of this particular program, but we weren't able to really talk too much about the trapezoid. But now we're here. Now, to answer the question, why is it that we have some of these f of x values being doubled and others not? Well, the way that I can demonstrate that is if you just give me a moment, I'm going to slide this particular screen here into my notebook. I want to move it over here. Let's make it a little bit bigger. And what we find here is that the f of x0, or the f of a is just indeed going to be the length of that particular segment. which would serve as the base of our first trapezoid, trapezoid number 1. But by the time we go to its right side base, that would be calculating the length of f of x 1. So whatever height that we have right here would be f of x 1. But why is there a 2? Because this f of x1 is going to serve double duty and serve as the base of the second trapezoid, or as one of the bases, the left-sided base, if you will. And you can see that as long as we are on the interior of this shape, let me even use a different color to maybe emphasize this better. These sort of pinkish magenta vertical strips, these are the guys that are going to get the extra 2 coefficient because they're going to serve as the bases of 2 separate trapezoids. But when we get to the end of this particular drawing with trapezoid number 5, right? This guy right here, the right side, is going to be our f of x n. Remember, we said that b is the same as x sub n, right? We said that a moment ago. Right? Whoops, I don't want to move that. But underneath this, we said that b was x sub n, and we will only use him one time. So hopefully that makes sense. Students should never get too upset about the ... here, because that just kind of indicates that we really could perform this rule on virtually as many trapezoids as we wanted to. But I got a feeling that your teachers are going to be probably pretty easy on you and just give you a very manageable number of trapezoids. All right, so hopefully that makes a little bit of sense, and we are able to maybe move into that example now. And tell you what, I'll even check out this program at the end of our example and see if our calculations were correct. So on to example 8. Which is the trapezoid rule approximating the area under sine of x above the x-axis on the interval 0 to pi using 4 trapezoids. Well, I'm going to go ahead and use that particular formula, but at the end of the problem, I'll kind of show you another alternative approach that one could use without having to memorize that thing. So we can say that the area, using the trapezoid, I like to use subscripts sometimes to denote which Riemann sum I'm going to use, would be equivalent to, well, we start off with b minus a divided by 2n. In fact, I'm going to go ahead and erase all of this information here so that it doesn't kind of get in our way. And I think I'm going to go ahead and do the same here. How about we get rid of all this markup so that I can move this over here and we can see our fresh formula. So we have b minus a divided by 2n to start things off. So the b minus the a would involve using 0 and pi, where 0 of course is going to be the a and b would be the pi. So we start off with pi minus 0 divided by, and then if you recall, 2 times n, or in this case, 2 times 4 is going to make up the beginning part of our formula. Next up, we put some kind of a grouping symbol, a bracket or a parenthesis, and the formula just says use f of x 0, which if you recall was going to be f of a in this case is 0, so f of a is the function up here evaluated at a. So that particular function would be sine evaluated 0. Now, just for the purpose of speeding up the video a little bit, I'm going to go ahead and write the name of the function evaluated at the specific x. All right, it's very likely that you might have a teacher that would require that you write that particular component in function notation first, and that's totally fine. I really feel that students should probably do one or the other and then maybe evaluate afterwards. So after we have sine of 0, we can see that we're going to be going to 2 f of x1. Well, f of x1, luckily for us, is already, well, the x1 at least is already on our screen. That's the pi over 4. So we now have 2 as our coefficient times the sine of that pi over 4. And again, I can't emphasize enough why the 2 is there. It's because this particular length is going to serve as a base for the first trapezoid as well as the second trapezoid. Okay. Last, if you're using function notation, you would write something like this probably. Okay, and this would just go on and on. I'm not going to worry about that anymore. I'm just going to continue down here and know that my next piece is going to be 2 times the sine of, yep, you guessed it, pi over 2. Continue that up with 2 times the sine of 3 pi over 4. Now we're almost to the end. We now have one last little piece here, which will not have a coefficient of 2 since it's our last base, and we would just say 1 times the sine of pi. And that would pretty much close out the blueprint, if you will, of the calculation that's going to give us our area. Now, for the rest of this problem, it's just really evaluating a lot of trigonometric ratios. So first, I'm going to simplify this beginning component and get pi over 8. Hopefully, we realize that the sine of 0 is 0, which kind of seems a little strange. The base of the first trapezoid is 0. Well, yeah, I guess there really isn't any height over here since the curve crossed the x-axis. So if you were really looking at what we were doing, it isn't so much using a trapezoid for that first shape as it is using a triangle. Sometimes that happens. You know, in some ways, triangles are very funny trapezoids. They're trapezoids that might have a base of 0. So you've got your next piece, 2 multiplied by the sine of pi over 4. Hopefully we are comfortable with the fact that the sine of pi over 4 is 1 over the square root of 2, or if you want to write that in a rationalized denominator form, that would be the square root of 2 over 2. And I'm going to be honest, I like the rationalized form. A lot of times in calculus, we sort of look the other way and we allow things, expressions to contain square roots at the denominator. But in this particular case, I like it rationalized, and you could probably tell why, because these 2's are going to cancel very nicely. We continue this process. When we get to sine of pi over 2, we know that that value is 1. You can actually see that somewhat from the picture. Then we have 2 times the sine of 3 pi over 4. Well, 3 pi over 4 has a sine ratio that's the same as the sine ratio of the pi over 4. Just in a different quadrant, but in quadrants 1 and 2, we know that sine is going to be positive. And then we go to our last piece, which is the sine of pi, which is another 0, right? 1 times 0, which is just still going to be 0. So when it comes time to do a little bit more simplifying, we can see that these 2's will reduce away, and we would essentially just have inside of the brackets or parentheses the square root of 2 plus the square root of 2, which could be 2 square root 2 plus 2. And it could be written like that. It's possible that you could factor out the 2 and do a little reduce with the 8, and pi over 4 times square root of 2 plus 1 would be fine. I'm going to switch the order and say 1 plus square root of 2, but it's the same thing. So any of these are going to be okay. I'm going to want to go ahead, just for the purpose of demonstrating something, I'm going to move to my calculator here, and I am going to maximize that. I'm going to go to a scratch pad so that I can do a little calculation here. I'm kind of curious, what is the decimal approximation for pi divided by 4 times 1 plus the square root of 2? And I know if I use the Nspire here, as long as I put a decimal place in my input, I'll get a decimal or an approximation for my output. So I end up with 1.896. Now that's going to be good to know. This is all equivalent to 1.896 to 3 places. So if I return to my Nspire, and namely my Riemann Sum program, so I'll hit home, back to current to open that current program. This particular program that my students now have in their calculators is very versatile because they can change this function. And I'm going to go ahead and see if we can do that. So one way to change this function is to double click on it, or you could hit the tab button to open up the function entry line. Sometimes it works, sometimes it doesn't. Had to make sure that I had this pane active. So if I go up here, let's get rid of all of this stuff and let's just enter the sine of x. Now, what's going to happen is we're going to have our window not so cooperative because, you know, our window's locked in at the various dimensions that it had given us. So what we can do is change those things a little bit. I can just go up to this 8. Oops, let's do it this way, in fact, because that 8's a little close to that function. We can go into the menu here and hit our Windows settings. And we can change that Y max scale, that 8 that was too big, maybe take it down to a 2. Now, on the X, we noticed that the highest X value that we had in our curve was really going to go up to like pi, which is 3.14. So what I might suggest here, I'm going to do something kind of funny. I'm going to maybe take mine to 4. Now that doesn't sound like that's a very logical thing to do because the sketch of a trigonometric function along the x-axis is normally sort of living in the world of radians, and using values that contain pi might make more sense. Well, that's not a big deal because I can just make that happen with my scale. So I'm going to make my scale pi divided by 4. What a great scale here to use because that seemed to be the increments that I was using. All right, so if I hit OK, now what I've got is a lot better representation of really what this problem was asking me to do. Now I have the ability to drag my A to be 0, and then if I can grab this B, bring it back to where it's equal to pi, right? And let me think here for a second. Yes, for a minute there I thought something was going wrong. Yes, we have 5 rectangles here, where in our problem we wanted only 4, so I just have to dial this back to be n equal 4. And then let's make sure that we are selecting the correct approximation, trapezoid. And there we go. There we have our picture. The only thing that kind of bothers me is that we still don't have the 5 trapezoids until I kind of tweak this just a little bit more. Let's see if we can get it locked into P4. I like that. I think that's our 4. 1, 2, 3, 4. Now let's see if our answer was right. The area approximation, 1.896, sounds awfully familiar to me. That's what we had right here. And if you're curious, the actual area under the curve is 2, which is something that can be done using the ideas of anti-differentiation. At the time of this video, my students haven't been shown that. It's likely if you're watching this, say, after we've gone through that unit, you'll definitely know that particular process. Or if you're watching this from another school, you may have already been introduced to definite integration. But anyhow, I think that pretty much sums up the video here. We were able to use this trapezoidal rule to find this particular area approximation. As I said before, if you don't want to use this long, ugly, and nasty formula, you can just simply go through the process of finding each of the 4 areas separately using a trapezoid rule formula 4 times. Now, when we get to my next example 9, I'm going to actually use that particular technique. So I'm not going to demonstrate it here, but if you watch the video entitled Trapezoidal Sums with Unequal Partitions, you'll see exactly what I'm talking about. So anyway, I hope this video helped. Good luck to you all, and I'll see you next time.